Welcome to this AS Physics tutorial on vectors. In this tutorial, Joshua will work through MCQs based on 20 past exams. If you don't have a PDF copy of this tutorial, you can contact us via the email address in the description below this video.
In question 1 it says, which statement about vector quantities is correct? In A, acceleration of free fall is a vector quantity, which we know is correct, because it has a constant magnitude. Now, it is a vector, but not because it has constant magnitude. It's a vector because it's a physical quantity with direction. So, even though the first part of the statement is correct, the second part is incorrect. So it's not A. In B and C, we have temperature and time as vectors, or given as vectors. And you should know that both temperature and time are scalars. In D, we have weight is a vector because it has direction. Now, weight is force. So we know that it's a vector. And the reason that it's a vector is because it has direction. So D is the correct answer. Then in number 2, which quantity is a vector? Here you need to know that momentum is a vector. Speed, temperature, and the Young modulus are not vectors, they are scalars. Let's look at number 3. Physical quantities can be classed as vectors or as scalars. Which pair of quantities consist of two vectors? We know that kinetic energy is a scalar. Force is a vector. So it's not A. Momentum is a vector, but time is a scalar. So it's not B. Velocity and electric field strength are both vectors. So the answer is C. In D, we have weight and temperature. We know weight is force, so it's a vector, but temperature is not a vector, it's a scalar. Then in number 4, which calculation produces a vector quantity? In A, we have current times time. And we know that this is equal to charge. Charge, of course, is not a vector. It's a scalar. In B, we have final displacement minus initial displacement. So when we take final displacement minus initial displacement, the answer we get is also a displacement, which is a vector. So we know B is correct. Work over time is power, which is a scalar. A half times the mass times the speed squared is kinetic energy. And we know energy is a scalar. So it's not D. Neither is it C. Then in question 5 it says, one object moves directly from P to R. So in this way, in a shorter time a second object moves from P to Q to R. So in this way, first from P to Q, and then from Q to R. Which statement about the two objects is correct for the journey from P to R? And we're given various options here. Now, the correct option is C. They have the same displacement. Remember that displacement is the shortest distance from start to finish. So, since both start at P and end at R, the shortest distance for both will be the same. It will be this distance. So it's C, they have the same displacement. Here it says an aircraft heads in a direction at an angle theta east of north with a horizontal velocity relative to the air of 800 kilometers per hour. So this is the aircraft's velocity relative to the air and our angle theta. The wind blows with a horizontal velocity of 200 kilometers per hour from east to west. The resultant velocity of the aircraft is in a direction due north. What is angle theta? and what is the magnitude of the resultant velocity. And we are given various options here. So we can start with a rough sketch. So we have the aircraft's velocity relative to the air. We must draw the wind's velocity and the aircraft's velocity head to tail. So this is 200 from east to west, and in this will be the resultant of the two. So the resultant velocity, which we know is due north. Now this angle here, of course, is 90. To find the resultant velocity, we can use Pythagoras. And this we can do on a calculator. And it comes to 774.6. kilometers per hour. So this will be due north. Now we can find theta here. So the tan of theta will be 200, or rather it's going to be the sine of theta. So opposite over hypotenuse. So 200 over 800. And we can find theta. So shift sine of 200 divided by 800. And it's 14.5 degrees. So we can check which is the correct option here. We definitely need 770 or 770 for the resultant velocity, so it's either A or C. And of course we worked out that the angle theta is 14. So it's going to be A. Here we have two forces, each of 10 newtons, acting at a point P as shown. So our two forces, each of 10 newtons. The angle between the directions of the forces is 120 degrees. What is the magnitude of the resultant force? So we can start by drawing these two forces head to tail. So 10 newtons this way and another 10 this way. And of course the resultant will be from the tail of the first vector here to the head of the second vector. So this is our resultant. Note that these two forces must be head to tail. And we need to find the resultant. Now, this force here makes an angle of 60 degrees with the horizontal. So we know this angle is 60. Then here we have an isosceles triangle. So these two sides are equal. And that means that the base angles must be equal. So this angle here is already 60 degrees. So these two must add up to 120. And it's an isosceles triangle, so each of them must be 60. Now we see that we end up with an equilateral triangle. All the angles are 60. And that means that all the sides must be equal. So the resultant here will be 10 newtons. And our answer will be B. Let's look at number 8. It says here, an aeroplane can fly at the velocity x when moving through still air. When flying in wind, the aeroplane's velocity relative to the ground is y. In other words, y must be the resultant of the aeroplane's velocity in still air and the wind's velocity. So basically what we're saying is y must equal x plus w, the wind's velocity. which vector diagram shows the magnitude and direction of the wind's velocity. Since y is the resultant of x and w, or must be the resultant of x and w must be drawn head to tail. And the only diagram in which y is the resultant of x and w, in other words, where x and w are drawn head to tail, is in A. So x and w are drawn head to tail, and y, the resultant, is from the tail of x, the tail of the first vector, to the head of the second vector, w. In question 9 it says, in still air, a bird can fly at a speed of 10 meters per second. The wind is blowing from the east at 8 meters per second. So the wind is blowing this way at 8 meters per second. In which direction must the bird fly in order to travel to a destination that is due north of the bird's current location? So we want this to be the resultant velocity. In other words, due north. We know that the wind velocity is 8 meters per second from the east. So this resultant velocity is the resultant of the velocity of the bird in still air, which is 10 meters per second, and the wind's velocity. So drawing it head to tail then, the bird would have to head in this direction, at this angle, theta. He will be blown off course by the wind, so 8 meters per second, in order to have a resultant due north. So these two must be head to tail. The bird's velocity in still air and the wind's velocity must be head to tail. And this is the resultant drawn from the tail of the first vector to the head of the second one. And we can use trig. We know this angle here is 90 degrees. So the sine of theta will be 8 over 10. And we can find theta shift sine of 8 over 10. And we get an answer of 53 degrees. Now, it's going to be 53 degrees east of north. This being north here, and this being east. So, east of north. So the answer here will be C. Let's look at number 10. The diagram shows two vectors, x and y, drawn to scale. If x is y, or x is equal to y minus z, which diagram best represents the vector z? So we know that x is y minus z, and we are looking for z. So the first step here is to make z the subject of the formula. So we're starting with x equals y minus z. I'm going to bring negative z to the left-hand side. It becomes positive. And the x we can take to the right-hand side. So it becomes negative x. So z must be the resultant of y and negative x. You can see this more clearly if you rewrite this equation as y plus negative x. So z is the resultant of y and negative x. And what is negative x? Negative x is basically x drawn in the opposite direction. So this is negative x. And we know that z must be the resultant of y and negative x. So we can draw negative x and y head to tail. Then the resultant will be from the tail of negative x, the tail of the first vector, to the head of y, the second vector. So this will be z. And our answer, of course, here is going to be A. It says here, the diagram shows two coplanar forces, P and Q, drawn to scale. Force R is given by R equals Q minus P. Which diagram represents R? We're going to start by rewriting this equation. as R equals Q plus negative P. So we can see that R must be the resultant of Q and negative P, since we are adding them to get R. Negative P, of course, is the vector P drawn in the opposite direction. So this is negative P. Since R is the resultant of Q and negative P, we need to draw Q and negative P head to tail. We can start with Q, and in drawing Q and negative P head to tail, negative P will go this way. Then the resultant will be the vector drawn from the tail of Q, from the tail of the first vector Q to the head of the second vector, negative P. And so our answer here will be C. Here it says the diagram shows two vectors, x and y. The vectors are perpendicular to one another. What is the magnitude and direction of vector x minus y? Now, firstly, x minus y, we can rewrite as x plus negative y. So the vector x minus y will be the resultant of the vector x and the vector negative y. Negative y, of course, is just y drawn in the opposite direction. So this is negative y. And to find x minus y, we need to draw x and negative y head to tail. So we can start with x, then negative y. This is 90 degrees. And of course, this will be the vector from the tail of the first one to the head of the second one. This vector will be the resultant. So this will be the vector x minus y. We can use Pythagoras to find x minus y. We know that y is 6 and x is 8. Then x minus y using Pythagoras will give us 10 newtons. We can find this angle here. We know that the tan of theta will be 6 over 8. And we can do this on a calculator. Shift tan of 6 over 8 will give us an angle of 37 degrees. Now we know that x minus y is 10 newtons, so the answer must either be A or B. And this angle theta equals 37 degrees is measured upwards from the direction of x. So the answer here will be B. Here it says the velocity of an object changes from an initial velocity u to a final velocity v. The vectors represent these velocities, so we have v and u. Which single vector represents the change in velocity of the object? So we need to draw the change in velocity as a vector. And we can start with the equation for the change in velocity. The change in velocity delta v is the final velocity v minus the initial velocity u. We can rewrite this equation as v plus negative u. So from this we can see that delta v is a sum of these two vectors, the sum of v and negative u. So delta v will be the resultant of v and negative u. And that means that we can draw v and negative u head to tail. So starting with v and then negative u. Of course, negative u is in the opposite direction to u. Then the resultant delta v will be from the tail of the first vector, so from the tail of v to the head of the second vector, so to the head of negative u. So this will be the resultant delta v, or the change in velocity. And from this, we can see that the answer is C. Here it says a ship is traveling with a velocity of 8 kilometers per hour in a direction 30 degrees east of north. What are the components of the ship's velocity in the east and north directions. We can start by drawing a diagram. So north and east. The ship is going at 8 kilometers per hour in a direction 30 degrees east of north. So 30 degrees east of north. And of course it's going at 8 kilometers per hour. Now, to get the easterly and northerly components, we can drop a perpendicular onto the easterly plane. Then the easterly component will be given by this vector. So we can call it VE. The northerly component, of course, is this vector. So Vn. Important to note that a vector is always going to be the resultant of its components. So VE and Vn are drawn head to tail. This angle here, of course, is 90 degrees. And this is 60 degrees. Now we can calculate the components. We can work inside this triangle and use basic trick. We know that the easterly component, VE, is adjacent to this angle. So VE over the hypotenuse 8 will be the cos of 60. And in VE will be 8 times cos 60. Now, on a calculator, this comes to 4. We can also find the northerly component. So inside this triangle, Vn over 8 is a sine of 60. And Vn is 8 times the sine of 60. On a calculator, this comes to 6.9. And the answer then will be B. Let's look at question 15. It says the arrow represents the vector R. So this is the vector R. Which diagram does not represent R as two perpendicular components? We're given 4 sets of perpendicular components. And we need to decide which set does not represent the components of vector R. Now, we can use the fact that a vector will always be the resultant of 2 of its components. And we can use the parallelogram method to find the resultant of each of these components. So using the parallelogram method, we complete the palm. In this case, it's actually a rectangle. Then this will be the resultant. In other words, the diagonal of this rectangle or palm with the same starting point as the 2 vectors in question. Let's do it for the rest. So completing the palm or rectangle. And drawing the resultant. So, which vector here does not look like the vector R? And of course the answer here is C. You can see that C is in a completely different direction to the vector R. Let's look at question 16. It says 2 dogs pull a sledge along an icy track as shown. So the 2 dogs. Dog X pulls with a force of 200 newtons at an angle of 65 degrees to the front edge of the sledge. So this angle here is 65 degrees. Dog Y pulls with a force of 120 newtons at an angle of 45 degrees to the front edge of the sledge. So 45 here. What is the resultant forward force on the sledge exerted by the 2 dogs? Now, in order to find the resultant forward force, we need to calculate the horizontal component of each of these forces. Also note that the angle here will be 90 minus 65, which is 25 degrees. And this angle here will be 90 minus 45, which is 45 degrees. Let's start with dog X. So dog X is pulling with a force of 200 newtons. And we want to find the horizontal component. This angle here, of course, is 25 degrees. And we want this component, which we can call Fxh, the horizontal component of the force that dog X exerts onto the sledge. And of course, Fxh will be 200 times the cos of 25 degrees. Let's do the same for Y. So dog Y exerts a force of 120 newtons. We want to find the horizontal component. So this will be the horizontal component, and we can call it Fyh. Of course, we know this angle here is 45 degrees. Then Fyh will be 120 cos 45. Now note that both these horizontal components act to the right. So to get the resultant of them, we need to add these two values. So the resultant forward force will be the sum of these two. That we can do on a calculator. So it's 200 times the cos of 25 plus 120 times the cos of 45. And we get an answer of 266.11. So 266.11 newtons. The answer then will be C. The answer here was rounded to two significant figures. So the answer is C. The diagram shows the dimensions of an elastic cord used to project a stone. So this is the cord over here, and we have the stone here. The tension in the cord is T when the cord is pulled into the shape shown. So the tension here is T as well as over here. Which force does the elastic cord exert on the stone? And we are given these four options. Let's start by looking at the diagram more closely. We know this angle here is 90 degrees, and so is this one. Then looking at the top triangle here, we can use Pythagoras to find the side width. And of course, this side will be 8 centimeters. This is a Pythagorean triangle. I'm also going to let this angle be theta. Then, since this whole length here is 16 centimeters, this must also be 8 centimeters. And in using Pythagoras in the bottom triangle here, we can find this length is 10 centimeters. Now we can see that the top triangle here is congruent with the bottom triangle. In other words, they have the same size. So this angle will also be theta. Let's look at the top tension. So we know the tension goes this way. We can resolve it into components. So T and theta. We have the horizontal component of the top tension here, which we can call H1, and the vertical component, which we can call V1. Now, H1 will be T cos theta. Now the cos of theta will be 6 over 10, which is 3 over 5. So it's t times 3 over 5. So 3/5 t. Then V1 will be t sine theta. And the sine of theta, of course, is 8 over 10, which is 4/5. So this is 4/5 t. Then when we consider the bottom tension here, we know that the bottom tension can also be resolved into two components. And I'm going to call the horizontal component H2. So this is H2. And the vertical component I'm going to call V2. Now, similarly, H2 will also be 3/5 t in this bottom triangle. And V2 will also be 4/5 t. So we see that numerically, the horizontal components are the same, as well as the vertical components. However, the vertical components are in opposite directions, so they will cancel. To get the resultant of the tensions in the chord, we have to add the horizontal components because they go in the same direction. So then the net horizontal component will be 3/5 t plus 3/5 t, which is 6 over 5 t. And the answer then will be B. Let's look at question 18. A force of 10 newtons and a force of 5 newtons act on an object. So 10 newtons and 5 newtons. The angle between the forces is 150 degrees. The resultant force on the object can be resolved into a pair of perpendicular components. Which row shows numerical expressions for a possible pair of perpendicular components? And we are given these options. Let's start by resolving these two vectors into their components, into horizontal and vertical components. We can start with a 10 Newton force. So we have the horizontal component here. I'm going to call it H1. And the vertical component, which I'm going to call V. This angle here, of course, is 30 degrees. So the horizontal component will be 10 cos 30. And the vertical component will be 10 sin 30. Let's go to this vector now. This vector is perpendicular to the vertical plane. So that means it doesn't have any component in the vertical plane. The vector itself is in a horizontal plane, so the horizontal component, which I'm going to call H2, will be the vector itself. So 5 newtons. Now we can find the net horizontal component. Now, taking to the right as positive and to the left as negative, we can see that H1 and H2 are in the horizontal plane. H1 is to the right. And since H2 is to the left, we have to subtract 5. So we have the net horizontal component and the vertical component as well, 10 sin 30. So let's look at these answers. The first one says 10 cos 30 minus 5. So this could be correct. However, we don't have 10 sin 30 for the other component. So this is incorrect. Now, there's no other option that has 10 cos 30 minus 5 and 10 sin 30. So the question now is, what do we do from here? Let's now consider a different set of perpendicular components for these two vectors. I'm going to draw a plane here, like this, and we have another plane perpendicular to it, this way. Let's work out the components of the 5 Newton force in these planes. Of course, we'll have a component this way and a component this way. This, of course, is 30 degrees here. So this component of the 5 Newton force will be 5 cos 30. And this component will be 5 sin 30. This angle being 90 degrees. Now, let's go to this vector. The component of this vector in this plane will be the vector itself, so 10 newtons. Then this vector is perpendicular to this plane, so it doesn't have any component in this plane. Let's find the net component in this plane. It will be 10 in this direction, minus 5 cos 30. Then the only component in this plane will be the 5 sin 30. So let's compare our answers here with the options given, 10 minus 5 cos 30 and 5 sin 30. And then we can see the answer is C. A velocity vector is shown. So we have the vector here. What are the components of the velocity vector in the northerly and in the easterly directions? And we are given these options. So let's draw the components. We have the northerly component, which we can call Vn, and the easterly component, Ve. Then, using basic trig inside this triangle, Ve will be 75 sin 30. And we can do this on a calculator. And it's 37.5. And of course, written with two significant figures, this will be approximately 38 newtons. Then the northerly component will be 75 cos 30. And we get an answer of 64.95. So then Vn, written with two significant figures, will be approximately 65 newtons. So 38 and 65. So the easterly component is 38. The northerly component 65. So the answer is C. Two cables are attached to a bracket and exert forces as shown. So we have a 15 Newton force this way, making an angle of 20 degrees with the horizontal, and a 6 Newton force this way, that makes an angle of 40 degrees with a vertical. What are the magnitudes of the horizontal and vertical components of the resultant of the two forces? And we are given these options. Let's work out the horizontal and vertical components of these two forces. So we can start with the 15 Newton force. We have the horizontal component, which I'm going to call H15, and the vertical component V15. This angle is 90. And we know that the angle here will be 20 degrees. So the horizontal component H15 will be 15 cos 20, and the vertical component will be 15 sine 20. Let's do the same for the 6 Newton force. We have the vertical component, which I'm going to call V6, the horizontal component, H6. This is 90 degrees, and the 6 Newton force makes an angle of 40 degrees with a vertical. Then H6 will be 6 sine 40, and V6 will be 6 cos 40. Now, important to note that the two horizontal components act in the same direction. They're both to the right, so we can add them. So the net horizontal component then will be the sum of these two. And we can do this on a calculator. And we get 17.95. So 17.95 newtons. Now, looking at the vertical components, the vertical component of the 6 Newton force is down, whereas the vertical component of the 15 Newton force is up. So to get a net vertical component, we must subtract these two. They're in opposite directions. Now, conventionally, we can use up as positive. So I'm going to take 15 sine 20. That's up. Down is negative. So 6 cos 40, I'll subtract. So minus 6 cos 40. We can work this out on a calculator. And we get 0.53. Now, 17.95 to two significant figures will be 18 newtons. So let's check which answer is correct here. 18 and 0.53. So it's going to be C. The diagram shows a force F. P is the horizontal component of F at an angle theta to F. So this is the horizontal component of F. Which graph best shows the variation with theta of the magnitude of P? And we're given these options. Now, we know that the horizontal component of a force F, in this case the horizontal component is P, is given by F cos theta. In other words, the horizontal component is described by a cosine function or a cos function. Now, important to note that all these graphs are given between 0 and 90 degrees. We know the horizontal component is a cos function, so let's look at the cos graph. We know this is what the cos graph looks like. And we are particularly interested in what happens between 0 and 90 degrees. So this section of the graph, we can see that it's a decreasing function. So which of these options are the same as this part of the graph? And of course the answer is A. So A. A glider is descending at constant speed at an angle of 15 degrees to the horizontal. So 15 degrees. The diagram shows the directions of the lift L, air resistance R, and weight acting on the glider. Which vector triangle could represent the forces acting on the glider? The important thing here is that the glider is descending at constant speed, and that tells us that the system is in equilibrium. So we have to draw these vectors head to tail in a closed vector diagram. So we can start with W, so straight down, W, and then R, head to tail. And then of course this will be the lift. So we have a closed vector diagram drawn head to tail. If you compare this drawing with the options given, we see that the answer is D. The diagram shows a ball of weight W hanging in equilibrium from a string. So we have the string here and a ball over here. The string is at an angle theta to the vertical, so this angle is theta. The tension in the string is T. The ball is held away from the wall by a horizontal force P from a metal rod. So we have the metal rod here and the force P. Which relationship between the magnitudes of T, P, and W is correct? And we are given these options. We can draw a force diagram of these three forces. We know that the system is in equilibrium, so we can draw these forces head to tail in a closed vector diagram. We can start with W, then we have P and T. And this angle here, of course, is theta. This is 90 degrees. Now we can consider each of these options in turn. In A it says P equals T cos theta and W is T sin theta. So we have both P and W expressed in terms of T. Let's do that by using this triangle. So we need to express P and W in terms of T. So W then will be T cos theta and P will be T sin theta. So option A will be incorrect because A says P is equal to T cos theta, whereas P is T sin theta, and W is T sin theta, whereas W is actually T cos theta. So it's not A. Then in B it says T is P plus W. Now we know that the system is in equilibrium, so the resultant of these three forces must be 0. The resultant is given by the sum of the three forces. So we know that T plus P plus W will be 0. The resultant of these three must be 0. Here we have T is equal to P plus W. But from this equation, we can see that T is actually equal to negative P minus W. So it's not B either. Let's look at C. It says T squared equals P squared plus W squared. We know that this is a Pythagorean triangle. So the hypotenuse squared, T squared, will equal the sum of the squares of the two short sides. So T squared, the hypotenuse squared, will equal P squared plus W squared. And so we can see that C is the correct answer. Why is D not correct? Let's look at this. W equals P tan theta. Now, looking at this drawing, the relationship between W and P, writing down this relationship between W and P, we know that P over W is the tan of theta. Then, making P the subject, we see that P is W tan theta, and in W will equal P over tan theta. So D is incorrect because this equation here is incorrect. W equals P tan theta, whereas W is actually P over tan theta. An object of weight 120 newtons is supported in equilibrium by two strings as shown. So we have the object here, the weight is 120 newtons, and we have these two strings. What is the tension T1 in the left-hand string? So we must find the tension in this string. Let's draw a force diagram. We know that the system is in equilibrium, so once again we can draw the vectors head to tail in a closed vector diagram. So we have the weight down of 120 newtons. We have the tension in this string going this way. And we know that this angle is 20 degrees. So immediately we can find this angle here. It'll be 90 minus 20, so 70. And then we have the tension T1 going this way. So T1. Now we can get this angle here that T1 makes with a vertical. We know this is 90 degrees and this is 70. So we know this angle here will be 20 degrees. So T1 makes an angle of 20 degrees with a vertical. So we can see that this angle here must be 90 degrees. Now we can find T1. So we know T1 over 120 is the cos of 20 degrees. And in T1 will be 120 cos 20. We can do this on a calculator. And it comes to 112.76 newtons. And we can see that this value rounded off gives us 113 newtons, so the answer is C. In a high wire circus act, a man of mass 85 kilograms is standing at rest at the midpoint of the wire. So over here, the wire on either side of the man is at an angle of 20 degrees to the horizontal. What is the tension T in the wire? So we can start with a sketch. So I'm going to draw the horizontal like this. We have the tension in this part of the wire, so going this way. And also the tension in this part of the wire, going this way. The angle that T makes with the horizontal is 20 degrees. And if you look at this point here, we see that we have alternate angles. So this angle here is also 20 degrees. In other words, this one here. And so is this one. Let's look at the horizontal and vertical components of the tension in each part of the wire. Since the angle here, or the angles here, are the same, and the tension is the same in each part of the wire, we know that the horizontal components must be equal in magnitude, and so must be the vertical components. And this, of course, is 90 degrees. Now, we need to find the tension T in the wire. There's also another force acting on the wire besides the tension. Of course, we have the weight of the man down. So the weight down. In order to find the tension T in this problem, we can take into account that the weight down must equal the vertical components up. Why is that? It's because the object or the man is in equilibrium, since he is at rest. So we know that the vertical components here are equal in magnitude. So we can add them, and the sum of the vertical components must equal the weight. So V plus V will give us 2V. This must equal the weight down. Now, what is the vertical component? It's going to be T sine 20. So twice T sine 20 must equal the weight down. And we know that weight is mass times gravitational acceleration. So the mass is 85 kilograms. G, of course, is 9.81. And we simply solve this equation. We can make T the subject. So it's going to be the right-hand side here. Divided by 2 sine 20. This we can do on a calculator. So 85 times 9.81 divided by 2 and also by sine 20. And we get an answer of 1,219 newtons. The answers here are given in kilonewtons. So if we divide this by 1,000, we get 1.219 kilonewtons. And written to two significant figures, we see it comes to C. A ladder rests in equilibrium on rough ground against a rough wall. Remember that rough means that we have friction. The weight W of the ladder acts through the center of gravity G. So the weight acts at this point. Forces also act on the ladder at P and Q. So at P and Q, these forces are P and Q respectively. Which vector triangle represents the forces on the ladder? And we are given these options. So let's look at the forces acting on the ladder. We know at point Q, the ladder is in contact with the floor. And so we'll have a normal reaction force acting up. So the normal reaction force of the floor on the ladder. We also have a normal reaction force acting on the ladder at point P. So the normal reaction force of the wall onto the ladder. Then the ladder will tend to slide to the left if it starts moving. So at Q here, the frictional force will be to the right. The frictional force will always oppose motion. At P here, the frictional force will tend to act up, since the ladder will tend to slide down here. So we can find the resultant of these forces. So at the bottom here at Q, using the parallelogram method, we see that the resultant of N and F here will act in this way, in this direction. And we can call it Q. At the top here, using the parallelogram method, we see the resultant will act this way. And we can call it P. Then, of course, the weight acts at G, and the weight is always straight down. Since the system is in equilibrium, we know that we should be able to draw all three forces here in a closed vector diagram with vectors drawn head to tail. So let's start with W. Then we have Q going this way. And we have P going this way. So P over here. Now we can compare our sketch with the options given. And we can see that here we have W down, Q going this way, and P going this way, all drawn head to tail. So the answer then will be A. So this option corresponds to our drawing here. An air conditioning unit is supported by a rigid beam PQ as shown. So we have the beam PQ here and the air conditioning unit. Which diagram shows the directions of the horizontal and vertical forces acting on the ends of the beam? So at P and Q respectively. And we are given these options. Let's start with point Q here. At Q, what would happen if we didn't have a bolt here? The beam would tend to slide down. The beam, of course, isn't sliding down, and that means we must have an opposing force up. So we have a force up at Q. Then at Q, the beam is attached to the wall, so it exerts a force onto the wall to the right. So the wall will then exert a force onto the beam, which is a normal reaction force to the left. So this angle is 90 degrees. What would happen if we didn't have a bolt at P? The beam would tend to slide from underneath the air conditioning unit to the left. And that means that we must have an opposing force to the right at point P. Then the beam also exerts a force onto the air conditioning unit up. And that means that the air conditioning unit exerts a force onto the beam down, which is a normal reaction force. So this is the normal reaction force of the air conditioning unit onto the beam. Once again, this angle is 90 degrees. Now we can compare this diagram with the options given, and we see that it's B.